So good evening. Uh, just a moment. Okay, so good evening everyone. So welcome to week 4 of the problem solving session for the NPTEL course Natural Hazards. So we'll get started. It's already 6:05, so we'll get started and then people can join eventually. So I'll be sharing the screen, and if it's not visible to you or if there is any issues, please let me know. I hope the screen is visible to you and you're able to hear me clearly. Okay. So as I said, this is week 4 of the problem solving session for this course. So in the previous class we had discussed uh, regarding the faults, then earthquake and such similar topics. So this week we'll be continuing with the earthquakes part. So we'll be starting with the seismic waves. So do you have any idea? Just a moment. Do you have any idea, like, you know, in simple terms, like what seismic waves are? Like, I have written a definition here, but what do you understand from that? Any idea, like anybody is familiar with this term, seismic waves? Or okay, so as it is written over here, it is the released energy travels outward in the form of seismic waves from the focus of the earthquake. So if you remember, I'll just try to do it in a schematic way. So let's say this is the surface, and the earthquake focus or hypocenter, that is the origin of the earthquake, is over here. So when that that slip happens, when that elastic rebound happens during an earthquake, or what actually happens is that this some sort of energy is released. So that energy is released in the form of seismic waves. So something is happening inside, and it is not a very small thing, right? So a lot of energy is accumulated and suddenly it is released. So that energy, it is released in the form of seismic waves. So this is released from the focus of the earthquake. So this is like emanating from the focus of the earthquake. So their behavior explains how we experience earthquakes and the kind of damage they cause. So these seismic waves, they have a lot to tell. So there are different types of seismic waves, so that I'll tell, but then what you have to understand is that each of the seismic wave has a story to tell, we can say like that. So the different types of seismic waves are body waves and surface waves. So just from the name, like if you're not familiar with this entire terminology, but like just from the name, what do you understand? Like body wave, surface wave. So what are these? You can just make a guess also, because the name, from that name you can make a guess. Body waves and surface waves. So from this uh, image, or at least you can just try to figure out like what it is. Any idea like what body waves or surface waves are? Yes, Kausalya, so you're right. So body waves, I'll get to the detail part, but then body waves are those which are, which are not evident on the outside, but then they travel through the like interior parts of the earth. That we can say. Like we don't see its manifestation on the surface, but then surface waves are the one which we are actually feeling. Like you see this ground shaking, all those things. That is actually a that is due to the surface waves, not exactly a direct impact of the body waves. So, as Kausalya said, there are different types of seismic waves. Like this is a broad classification, but then these are again further classified. So in body waves, we have the P waves and the S waves. So P waves means the primary or the compressional waves which arrives first. So suppose let's say uh, this is the surface and we have the hypocenter or the focus over here. So when the earthquake strikes and this energy is dissipated, the first one to come out will be the P waves. So P waves will reach first, like they are the ones to come first, and they are called as compressional waves. And I'll tell you why that is called. So that is, if you look at this image, you can see this is how the motion is happening because of a P wave propagation. So P wave you cannot see on the surface, but then this is how it is. Like if you look at this diagram, these electric lines, they are a point of reference. So as you can see, they're broken over here, right? But if it was normal, I'm not drawing it very properly, but then yeah, if it were a normal situation, the electric lines would have been intact like this, right? So if they are broken, which that means they are stretched and then they are compressed. So that is what you're seeing here. So here they are being stretched. That is known as dilation, and it got broke. And where it is compressed, the electric lines have come closer. Again, they are dilated or they are extended, so they are broken, then compressed. So this is the normal condition, and this is what you see when a P wave propagates. So are you getting the point, or do you want me to repeat this? I hope you are understanding this. Like I'm not sure if Professor Malik has explained like in that detail. That's why I just put it here. Like this is a just a basic understanding of what earthquakes are. Although your course is mainly focused on its effects, but then you need to understand how it works. So that's why. I hope you are getting this point of regarding P waves. So P waves are primary or compressional waves which arrive first. So whenever an earthquake strikes, this is the wave that is recorded first. Okay. Then we have S waves. So the P is the primary wave and S waves, they are the secondary or shear waves. So in case of S waves, when compared to P, this is slower. So in comparison, we are not saying like S wave is very slow or anything, but in comparison to P, it is slower, but it is destructive. So whatever wave might be, but then this is destructive. So in this, if you see the motion, if you remember in case of P wave, the motion was kind of this stretching like this, and then you have a compression like this, right? So it has a motion somewhat like this. So it's like the movement is side to side. There is no further movement. But then in case of S wave propagation, the same electric line, if you see, you can see how it is moving, right? So it is moving in this fashion. So this is how the S wave propagates. So it can cause even more destruction. So it is actually, in the earlier case, if you remember, displacement is there, but it's like not very obvious. It's along that line. But then in this case, it's like, it is pushed from one side to the other. So that kind of extensive movement is caused by the S wave or the secondary wave. So these electric lines are just for your point of reference to tell you how the S wave propagates. So there is a vertical movement and also we can say a horizontal movement also. Then comes the surface waves. So surface waves are of two types. So like how body waves are of two types, like P wave and S wave. Surface waves are of two types. We have the Rayleigh waves and the Love waves. And both of them are like mostly they have a kind of a rolling motion. In case of Rayleigh wave, we call it as elliptical retrograde motion. I don't think you require the terminology, but just have to understand. Love wave is a bit similar to the S wave, but then um, it is more, you can actually experience it on the surface compared to the S wave. So on the surface, that motion is very much evident. So this is the love wave. And in case of Rayleigh wave, that is the elliptical retrograde motion or a rolling motion. So it's completely, this Rayleigh wave is the one that you can actually see when a earthquake strikes. Like, I'm not saying the you can see the wave as such, but you can see the effects caused by this wave. So these are the two types of surface waves. I have put the reference over here, the textbook that I had taken this picture from. So if you need further explanation, you can go through this. This is the Natural Hazards and Disasters from by Hanman D, 2016. So this is again an image similar to the previous one. Again, if you look at the electric fence, you can see how the land has moved, right? So it's very much obvious in this particular case. So this is how the surface wave propagates. So that whatever movement is there, that is very much evident on the surface. Thus the name. So this brings us to the next part. Okay, I have a video actually, so I think that might help you have a visual memory. So yeah. So I hope that kind of summarizes what I've been telling. So then we'll come to the next part, that is, which is already mentioned in the video also. So that is regarding seismographs. So seismographs, they are instruments which are used to record the motion of the ground during an earthquake. It's basically, as I said, you have four kinds of waves, right? So in the seismograph, this P wave, since it is faster than all the other waves, that is recorded first. Then S wave is recorded, and then the surface waves are recorded. So seismograph is the instrument which records this motion, and seismogram is the recording of the ground shaking at the specific location of the instrument. So this is a seismogram. So don't confuse with it. Seismograph is the instrument and seismogram is the recording. So, if you look at this one, you'll see amplitude of the wave versus the time. So, you can see the first one to be recorded is the P wave. So, its amplitude is not much, like as I said, the effect of surface wave as you progress from P, S, Love and Rayleigh wave. So, you can see as you go further, the effect is more. So, amplitude is more. So in case of P wave, that is the first one to be recorded. That is followed by the S wave. Then it is followed by the surface wave. So you can see the difference, right? So this is a seismogram. Seismograph is the instrument and seismogram is the recording. So this is a seismogram for the 1906 San Francisco earthquake, and it shows the arrival of the main seismic waves in sequence, P, S and surface waves. This is also from that book only, so you can actually refer. It's a very, it has good illustration, so I think it'll be easier for you to understand. Like if you need more information regarding all these, natural hazards and how they are formed, all those things. So, like it has very good pictorial representation. So I told you like from where the earthquake comes, and the seismogram is generated by the seismograph. So all these things we know. So how do scientists locate the earthquake location? Like people say, right? Originated from this place, and then all those details. So how do they do that? So that is done by this triangulation method. I have a video in the subsequent slides that time I'll show you. But the basic thing is that there are different stations having seismographs. Okay, so we have in this diagram, if you see this green, blue and red, there are three different stations. So what they do is they will first calculate the difference in the arrival time between the P and S wave. So P is the primary wave which comes first, and S wave is the secondary wave which comes immediately after the primary wave. So what they will do is, if you look at this, so in Mexico, this TEIG, the SOCO and SSPA, so what they did is, since TEIG is pretty close to this epicenter, I will tell you how this is calculated, but if you look at this image, since TEIG is very close to that, the P and S wave, that interval is quite less, because as soon as the P wave came, within no time the S wave also arrived. So that difference is first calculated, and then keeping that difference as the radius of a circle, they will draw the circle around this area, and then where the point of intersection of the three circles, so you can see this blue circle is there, this green circle is there, and this red circle is there. So they all intersect at this point, and then they deduce this as the epicenter of the earthquake. So not exactly the hypocenter, but then of course hypocenter is directly below this epicenter, but then this is how they determine the earthquake location, like from where it has come. So this actually helps them in understanding, the extent of destruction that that earthquake has caused and can cause in the future in that area. So I have a very good video coming up, so I think that can also help you in actually understanding what I have told you. But then the basic thing you have to understand is that in order to locate an earthquake, we need three seismograph data. We need to understand the difference in the arrival of P and S wave, and then making use of this, we will plot three different circles, and then when the point of intersection of all these three circles is your epicenter, or then if you extend it further, that is your hypocenter or focus of the earthquake. I hope that is clear to you. As I said, you can always interrupt me in between, there is no problem. The basic thing is that you need to understand what I am trying to convey. So if there is any questions, any doubts, please feel free to ask me. So we talked about how to locate the earthquake. Then we are going to talk about the earthquake intensity. So, for a layman who doesn't know the scientific explanation regarding an earthquake, so suppose there is a person in a place, let's say Nepal. Now, recently there are so many earthquake events recorded there. So, let's say a person is there in Nepal, and then he or she is experiencing this earthquake effect, which is basically the shaking and all those things. So, they what they experience, like if they see a lot of trees falling or buildings collapsing, like what they see, the extent of destruction, that is known as the intensity. So it's actually a qualitative way of talking about the earthquake. Like if an earthquake strikes, it might not be a very big one in terms of magnitude. Of course, I'll tell you the exact difference what it is, but then in terms of magnitude it might not be very big, but then in terms of its effect in that particular area, it might be very huge. So in that term, we use it as the earthquake intensity. So effect of an earthquake on the earth surface is what you call as the earthquake intensity, and this is not quantitative. So you might be reading in the newspaper that 7 magnitude earthquake, 6 magnitude earthquake, that is earthquake magnitude. That is not earthquake intensity. Earthquake intensity is a qualitative factor, and it is based on how people perceive it. Of course, it's not that one person feels it in this way, the other person. A general idea has been made, and then people have come up with this modified Mercalli intensity scale. So it is a 12-point scale in which the lower numbers they indicate how the earthquake is felt, and higher numbers are based on the observed structural damage. So I think I have a figure of that one. Yeah, so you can see, right? So I think in the Mercalli scale there were 12 points, and in the modified Mercalli scale you have the 10 intensity scale. So you can see, right? The first one, the shaking is not felt, so you don't feel the shaking, but then maybe this was recorded somewhere by a seismograph. So that is intensity 1. But then as the intensity number progresses, let's say we come to 2, 2 and 3, it's not very much, but then it's felt by very few people. Because recently, I'm currently in Uttar Pradesh. So recently, I think during the Nepal earthquake, sometime during that, many of my colleagues, they said that they felt an earthquake when they were sleeping, but then I didn't feel it. So that is like, it depends on the kind of people, right? So that is what they're saying, felt only by a few persons at rest, especially on the upper floors of buildings. So not everyone might have felt it. Then as you go further, let's say in intensity scale of 6, you can see that is felt by all. Everybody experienced it. Many got frightened. Some heavy furniture moved. A few instances of fallen plaster, and damage is slight. It's not very much. And then if you look at 9 or 10, you can see damage is very high, and almost structures are destroyed. People might have been affected, so all those things. So you can see as you go from 1 to 10, the effect of that earthquake is tremendously felt towards the end. So this is the Mercalli scale. So Mercalli scale talks about the earthquake intensity, and not the number that you see in papers when an earthquake strikes. This brings us to earthquake magnitude, which I've been talking about. So earthquake magnitude is the Richter scale or Richter magnitude scale, which records this earthquake magnitude. So based on this, how they mainly base this on the ground motion, the amplitude of the ground motion and all those things, and this is based on a logarithmic scale to the base 10. So it's basically each level is 10 times stronger than the previous. So if you say 1 to 1.9, that is a micro earthquake, you can say. It's not very intense, and most of the time you don't feel it, but it might still be going on, so you don't know. So that is 1 to 1.9. So then when you come to 2 to 2.9, that is a minor earthquake, we can say. But just if you look at this, by number it has increased by 1 only. But then in terms of this earthquake magnitude, this is actually 10 times stronger than the first one. So as you go each level, you have to understand, like, this is 10 times, this will be 100 times stronger than this one. So, like, it's multiplied by 10. So you can imagine how earthquake of magnitude greater than 9 might be, right? So if such an earthquake strikes, it will cause tremendous damage to life and property. That's a very, very risky condition to be in. So that is the difference, okay? You have the earthquake intensity, then you have the earthquake magnitude. Earthquake intensity is a qualitative interpretation of that earthquake, and earthquake magnitude is the quantitative one. Here you have a number. People tell this much magnitude earthquake struck this much, so they know. But in case of the earthquake intensity, we are actually talking about how people feel it. So that is actually a qualitative thing. You don't have a number there. People can feel it in very different ways. So it's not a very, that's just like a first-hand information about that earthquake. But then the actual one is the earthquake magnitude. So you can take a look at this. So here, an earthquake of magnitude 6 registers with 10 times the amplitude as an earthquake of magnitude 5 from the same location and on the same seismograph. So you can see, right? So this is 5. And in terms of number, it has just increased by 1, like 5 plus 1, and the magnitude is 6. But then in terms of amplitude, it has increased 10 times. So that is what they have written here. 10 times the amplitude as an earthquake of magnitude 5. This is from the same location, and it is recorded by the same seismograph. So this is the, what do you call this as? This graphical representation, what do you call? Anyone? I just mentioned it. The instrument is seismograph, and what does it? The answer is there on the description also. Okay, the answer is seismogram, as you have given me. Seismograph is the instrument. Okay, seismograph records this. Seismogram is the what you are seeing here. This graphical representation is the seismogram. So this you can see, right, what they have written here. An earthquake of magnitude 6 registers with 10 times the amplitude as an earthquake of magnitude 5 from the same location and on the same seismograph. So this difference on the Richter scale, it is just 1. But then, by the amplitude, if you compare the amplitude, that is like 10 times difference is there. I hope you have understood this, what I'm trying to say regarding the magnitude difference. So you should not think that, in a place a 4 magnitude earthquake struck and a nearby place, let's say a 5 magnitude earthquake struck. So you will be like, oh, it's just a one scale difference on the Richter scale. So what large thing might have happened? But that's not the case. Like that amplitude is significantly higher. So the effect will be more in case of magnitude 6. So this brings us to predicting earthquakes. So this has been a point of interest for as long as we have known earthquakes. So it's not very easy to predict earthquakes like very accurately. For instance, let's say if unlike cyclones for that matter, like let's say a cyclone, a low intensity, a low pressure zone is formed in the Bay of Bengal or Arabian Sea or any ocean, let's say. So this meteorologist or people in this climate science, they might note this one, and they can actually based on several studies and things, they can actually say like where this cyclone might go and how big it can be. Like unlike the earthquake, they can actually predict, and some sort of manner they can say like how long, especially people near the coast, definitely they have to be relocated. But then if it's a very huge cyclone, then they can say, okay, this much kilometer from the coast people need to move. So that way, that prediction is much better when compared to the earthquake prediction. Earthquakes are not very easy to predict, but then studying certain things we can actually expect that an earthquake can strike in this area, so we can actually be prepared for it. So that is some ways are there. So first one is tracking fault movement using global positioning systems. So can somebody tell me what a fault is and what the fault movement is? We had discussed this in detail in the last class. I will recap it again in this towards the end of this class. But then, who all were there? Just what is a fault and what do you mean by fault movement? Just you can make a guess also, like if you don't remember. In terms of earthquake, like I had drawn and shown you also, no? So just give it a try. Like let's see how well you remember. You can actually put it in the chat box also. Like if you're hesitant to talk, you can put in the chat box. I don't want very big definitions. I just want to understand how much you have understood. That's all. What is a fault and what do you mean by fault movement? Like a fault moves. How does it move? Like there are different ways it can move. Please give it a try. Like just put it in the chat box. I don't mind. You don't have to talk. You can just put it in the chat box. I'll look into it. Yeah, fault can be called as a fracture also, like Kausalya has put. So it's basically a zone of weakness in the earth. So it's thank you so much for responding. So that's the thing. So it's a zone of weakness. And what all kind of movements does a fault have? I just need the names. I don't want the definition or anything. We had discussed few movements, right? How the fault can move up, down, at an angle, or side to side, whatever. So there are certain terms, just those three broad classification, that's all. Okay, so maybe some of you might know, but for those who don't know, I'll just say. So as Kausalya also said, it's a zone of weakness in the earth, inside the earth. So let's say this is the surface, and this is the zone of weakness. So this is inside, okay? This is like a cross section. So this is one side of that block, and this is the other side of the block, 1 and 2. So if this is the zone of weakness, then 1 or 2 can slide over the other. So if 1 goes down, okay, if this is the movement, 1 goes down and 2 goes up, what do you call it? Yeah, these are called like hanging wall and foot wall. So if this is the hanging wall, so when the hanging wall goes down, what kind of fault is it? Hanging wall can go down, hanging wall can go up. So when hanging wall goes down, what do you call that fault? Yes, so it is the normal fault, and just the opposite, we call it as the reverse reverse fault, or if it is a low angle reverse fault, we call it as the thrust fault. So I just said this because I just wanted you to recap this. It's easier because this term will constantly come when you're talking about earthquakes. This fault movement, fault. So you need to have an idea what they're talking about, what kind of movement they're talking about. So basically, this tracking of fault movement using global positioning system. So all of you are familiar with this GPS, right? Many of you are using it on your phone. So what people, especially seismologists, what they do is they know where a fault is present. Okay, so what they will do is they will put these GPS or global positioning systems in different locations, and they will monitor its movement, basically the change recorded in that GPS over time. So they will know how, in what rate that fault is moving. Is it moving very fast? Is it moving very slow? Or based on that, actually, they can see or they can talk about an impending earthquake, like if an earthquake can strike in the near future. So it's not very accurate. Like they might record a movement, but they don't know when that energy, like how much that energy is accumulated and at what point of time that is going to be released. But they can broadly say around this much time you can expect that something is going to happen. So this is one way by which seismologists monitor the uh, earthquake prone areas. And then this brings us to the foreshocks. So foreshocks is basically, it's not, actually you cannot talk about prediction. We can say it's prediction of a main earthquake event. So that is like foreshock is are those earthquakes which occur prior to a main earthquake event. In the sense that foreshocks compared to the main earthquake, let's say the main earthquake is of a magnitude of 7, let's say. Okay. Then the foreshocks might not be of that much magnitude, but they will precede most of the earthquakes. And large earthquakes, this is also a case. So that's why, as I said, predicting earthquakes is not very easy, because most of the earthquakes are preceded by foreshocks, but then large earthquakes of magnitude 8 or 9, if you take a look at that, that can occur with no foreshocks. So you are like all of a sudden you are taken by surprise. But the problem with this is that foreshocks and small earthquakes, they are not easily distinguishable. You cannot, if earthquake strikes, you cannot be sure whether it is a foreshock or if it is just a small earthquake. You will realize it later on when a major earthquake strikes. But then most of the time what people do is that foreshocks might be a bit frequent. Like if you look at the timeline, a particular area might be experiencing frequent earthquakes. So I'm nobody to say it for certain, but then this Nepal area, like this northern part of India, recently it has been experiencing isolated earthquake events. So since we are a bit closer to the this Himalayan, that fault region, so maybe these are foreshocks. So it's not sure. Like they can be small earthquakes, but then we cannot rule out the possibility that these are foreshocks for a major earthquake event in the future. So such things. But then, as I said, there is a lot of uncertainty. You cannot for sure say that this much magnitude earthquake will strike at this time or nothing. You just have to, these things just help you to expect an earthquake event and be prepared for it. That's it. Then another method of predicting earthquake is the radon gas concentration in the soil or groundwater. So you know about radon gas, right? That is a noble gas. So its concentration in soil or groundwater is monitored. So radon is, you don't have to go into detail, but you have to know that uranium, lead. So they are like those who are interested in this nuclear things, they might be knowing. So these are radioactive uh, elements. So uranium, lead. So uranium will eventually transform to lead. That for the time being, you just have to know that. So when that process happens, in one step, radon is also formed. Okay, like it's a series of, that is why we call it as decay chain. So when uranium decays to lead, in one of that, one part of that chain, radon is also formed. So this radon, it does not form any chemical bonds and it will remain mechanically trapped within the rocks. So mainly this uranium that we are talking about, it is found in the rocks. and this decaying, all these things are happening within the rocks. So when radon is formed, that cannot attach to any other elements or anything. So like no complexes, no chemical bonds are formed, and they will get trapped within the rocks, and they will escape along the fractures. These weak zones, they will escape. So they are not bound anywhere. So when these fractures are, if people are studying an area and they find that the radon gas concentration is high in that area, like they studied the soil or they studied the groundwater, and they are saying radon gas is more, that means there is a fracture in that area. And if a fracture is there in that area, you can expect a fault movement, or in a broader sense, you can expect an earthquake event. So that is how radon gas is used. Then ground elevation changes. So rise of few centimeter in surface elevation above the fault. So as I said, let's say if this is one block, and let's say this is how initially it was, okay? So this is 1 and this is 2. Then after a period of time, one slightly moved up. So like it's a very, very negligible movement, but then centimeter scale you can say, but there is a movement. So this one moved a bit up. So that elevation change can be seen on the surface. So as such, for somebody standing on the ground may not understand, but then people who are studying all these things, they will look, using certain instruments and machines, they can understand this. So when that ground elevation change is there, that means that fault is moving. And if the fault is moving at one point of time, that is going to release a lot of energy. So that's how ground elevation is used. Then similarly, groundwater level changes also. So if there is a drop in the water table, that kind of tells you that the water has gone into a few fractures or weak zones, and which can later manifest as a earthquake, or like that movement can later manifest as an earthquake. So these are few ways in which an earthquake can be predicted, but not very accurately. So the first one is the GPS thing. Then you have the foreshocks. Then you have the radon gas concentration in soil or groundwater. Then you have the ground elevation changes. Then you have the groundwater level changes. So as I said, however, short-term forecast or early warnings raise complex political issues. The problem with this is that nobody can for sure say when an earthquake is going to strike. But if seismologists are seeing a lot of these evidences, like maybe radon gas concentration has increased, maybe the ground level has increased, anything, and they're saying, okay, if they inform the higher authorities that this area might experience an earthquake in the near future, so please do the necessary things. And if people if the authorities do all the things and be prepared for the earthquake, and if the earthquake never strikes, that is like it's going to create a lot of it's going to cost us a lot. So such issues are there, but at the same time, that uncertainty, even with the uncertainty, it is always better to be prepared rather than face it in the later time. So that is why like most predictions are false alarms, but then it's always better not to ignore the predictions also. Like it's better, right? And it is expensive and disruptive. This brings us to earthquake probability. So this is not exactly prediction. Prediction is like altogether a different thing. But earthquake probability is that, as if you remember from the previous classes, I had shown you this world map in which I said that the plate boundaries are where you have the subduction zones or you have the mesoceanic ridges. Wherever you have the plate boundaries, those areas are prone to earthquakes or volcanic eruptions. So right, this area there is a probability, huge probability that these areas are definitely going to face an earthquake or any natural hazard at any point of time. So in this case, although specific predictions cannot be made, reliable forecasts about location and frequency of events can be made. So there might be such places, for instance, if you go to South India, like southern part of India, that area is not very prone to earthquake. Like some isolated incidents might be there, but then not as frequent as the northern part of India, which is very close to the Himalayas. So people living close to Himalayas need to be more much more prepared than the people who are living in the southern part of India, because this area is very much prone to earthquakes. If you look at the past events and near present events, that area has experienced a lot of earthquake. So that's how we cannot make specific predictions, but reliable forecast can be made. Like how you look at the weather forecast, right? People say that there is a chance for rain. Rain can come, rain may not come, but then there is a chance. That's the thing. Awareness of tectonic environments can help scientists in quantifying risk for different regions. So this tectonic environment, as I said, like the subduction zone, water, like based on this plate position, plate movement, all those things, if scientists know it for sure, they can at least reduce the risk, quantify the risk, and then reduce the casualty in different regions. Past event records can help determine frequency of future events. So if you see a place which every year it is experiencing one or more than one like earthquake events, then you know that you are supposed to expect earthquake events in the subsequent years also. Or if one area, let's say at an interval of maybe oh, like for 1 year, let's say in 2000 earthquake struck, then you have an event in 2004, then you have an event in 2005, then you have an event in 2009. So somehow there is a 4 to 5 year gap is there, right, between each earthquake event. So in the next 4 or 5 years, you can again expect an earthquake event. So that kind of probability we have to take into consideration. So that is how past event records can help determine frequency of future events. So this is a world earthquake risk map, which is based on the peak ground acceleration. Peak ground acceleration is like the movement associated with the earthquake. So you can see here, right? Again, if you recollect that map which I had shown in the previous sessions, you can see where the plate boundaries are, where the subduction zones are. If you look at the Himalayan region, you can see how high or how dark that color is. And if you look at southern part of India, like Kerala, Karnataka, Maharashtra, those areas, so you can see it's like green to, this area is completely white. So you can see how less prone this area is, and then compared to that, how highly prone these areas are to the earthquake. So across the world we have this map, but of course, like with advancement in technology and everything, maybe we can find something else and then bring down this confusion regarding whether it is going to strike or whether it is not, or whether this, like how, like with advancement in technology, you can be a bit more accurate with these predictions or determining the probability. So minimizing the earthquake damage. So this is basically, earthquake is going to strike. There is nothing that you can do to not let an earthquake strike, right? So earthquake will be there, but then the better thing that you can do is, in order to minimize it, the damage caused by the earthquake, or if you remember from the first session, I said, like, you have natural hazard, you have natural disaster, you have a catastrophe. All these three terms are actually based on how loss to life and property has come about because of a event such as an earthquake or cyclone or volcanic eruption, anything, or landslide. So let it be anything, but how much of damage it has caused. So that damage, if we can reduce, at least we can live with this, right? So that is why you have to minimize the earthquake damage. So earthquakes do not kill people. So when the ground is shaking, that is not killing anybody. What is causing the casualty? The falling buildings, the fire associated with the collapsing of highway structures, everything. These are the reasons why people are either injured or people lose their lives. So as such, earthquake is not creating an issue. So the best thing that you can do is be better prepared. So better preparedness is necessary. So the this is very well done in Japan, because Japan is very much prone. Japan is in the subduction zone, so it is very much prone to earthquake. It is prone to volcanic eruption, tsunamis, all kind of thing. The Japanese has to face, but still they, you don't see them struggling for a long period of time to recuperate. So the reason is that they are better prepared. So they build this flexible, well-built wood frame houses. So if you look at the videos on YouTube or on images on Google, you can see that the Japanese house structure is very much different from our houses. We have these concrete houses. They also have concrete structures, but they build it in order to, so that it can accommodate the energy which is released during an earthquake. So they built flexible, well-built wood frame houses. They may get damaged but are not likely to collapse on people. So that if that structure is strong, inside damages might be there, but then it will not collapse and kill further more people. So that much guarantee they can give. Then we have seismic retrofitting. So that is basically strengthening a structure to make it more resistant to earthquake shaking and damage. So that is basically, you can bolt a structure to the wall or to the ground, so that when an earthquake strikes, this will also shake along with it rather than falling down. So it is seismic retrofitting. I think I have an image also. Yeah, so this is retrofits. So you can either block like this, you can double top. So basically you are making that structure very much intact, so that it doesn't collapse. See, foundation bolts are there. So people are bolting their structure to the foundation, so that that entire thing doesn't fall down. Then we have base isolation. So this is basically a method of seismic protection where the structure is separated from the base. So most of the time what happens is, if the structure is attached to the foundation, when the earthquake strikes, this is going to collapse. But if it is able to move on the foundation, then it will shake along with the earthquake and it will not fall down. So by separating the structure from its base, the amount of energy transferred to the superstructure during an earthquake is reduced significantly. I don't know if I have a photo or a video. Let me just check. I think yes. In this image, if you see, this is the same thing. So here they have created these pillar-like structures. So what actually happens is that during an earthquake, this structure will move from side to side with the earthquake. If it were not done in this manner, this entire structure would have collapsed down. But because it is fixed in this manner, and this some kind of springs or something is there, I don't know the exact technology associated with it, but then it will move along with it, so that maybe this chairs or such small things might collapse within the structure, but then the structure entirely will not fall apart. So these are again, if people do all these things to protect their house. So you can see furniture is bolted to the walls, because most of the time when furniture collapse on top of you, you get injured, right? So furnitures are bolted. Steel brackets will anchor the chimney, so the chimney won't collapse. Then this straps bolted to the wall studs, so you can see these straps are there. Then the steel frame and anchor bolts are added, so the structure can stay intact. It will not collapse that easily. Like if it's a huge magnitude earthquake, then that can also cause some issues, but otherwise these are sufficient to hold the structure. So last class, if you remember, I had talked about soil liquefaction. So I got a good video of that one. So I have included it in this one. So have a look at this. So I think that gives you a very good explanation regarding soil liquefaction. If you have any doubt, you can ask me right now, because I have seen sir mentioning this in a lot of his slides. That's why I just put this video inside. Even I have another one showing you the soil sand boils, which is also surface manifestation of this liquefaction that has taken place during the earthquake. I think Professor Malik has also shown really good images from field showing these sand boils, but you can have a look at this, how that is happening. So this is a cross section of this area. So when an earthquake strikes, the ground is settling down, water pressure is increasing, and there is a weak zone is created, and whatever that liquefied wet sand is there, that is coming out. So this, in reality, it manifests like this. So they had just shown it as in an animation. So this is from the Loma Prieta earthquake in 1989. So sand blows or sand boils. So this is not actually, if you see it on the surface, it's not just just from the surface below, but it's actually coming from a bit more deeper part. That is the sand boil or the sand blows. So surface manifestation of the soil liquefaction or densification process. There is another one. I had mentioned that also. So what is that? Like just like sand boils, because of sand, the soil liquefaction. Another thing also you can see on the surface during an earthquake. Can anyone tell me that? It was mentioned in the previous video also. You see the structure separated in blocks kind of thing. I had shown an image also in the last class. If anyone can recollect and tell me what was that? Just like sand boils, there was something else, in which, if you remember, if the ground was initially like this, because of this liquefaction, the ground, it became like this. I hope you get the idea. So what do you call this process? Please try to recollect, or in the previous video also I think they have talked about this. Anybody? This is known as lateral spreading, if you remember. So if the top surface is a bit intact, but the bottom surface is moving, then it will kind of break the top in different blocks and spreads apart. So it's called as lateral spreading. Laterally it is spreading. So this brings us to the problems part of the today's session. So let's get to it. It's basically a bit of a recap and then related questions also. So you can just try to give me the answer. So the first one is, the fault type which involves the horizontal movement of blocks past each other is known as. Those of you who understand the question, you can give me the answer. For those who didn't understand the question, you can ask me. The fault type which involves the horizontal movement of blocks past each other is known as. So there are two blocks, they are horizontally moving. What do you call it? Please don't hesitate, you can just tell me. Even if it is wrong, that is fine. I can explain it again, but then please give it a try. Yes, as Kausalya has put it in the chat, it is the strike-slip fault or strike-slip movement. It is strike-slip fault. So this is basically, you have Okay, just a moment. Okay. So let's say you have a this is a three-dimensional representation. So this is the fault, the three-dimensional fault interpret this thing. So it's like this. So if this block move past this block, then it will become, please wait, I'll just plug in my laptop. Okay, so as I was saying, so this is a strike slip fault. So in this block is moving in this direction and the other block is moving in this direction. So there is a horizontal movement. So that slip is there. That is why it is a strike slip fault where you have the horizontal movement. If you have the movement vertically, what do you call it as? Like you have strike slip movement, you have another one uh, where you have this uh, not horizontal, not vertically, like at an angle, you can say. The other classification of movement along a fault, you have strike slip fault or strike slip movement. Similarly, you have another dash slip movement. So what is that dash? At an angle if it is moving up and down. So if it is moving at an angle, like if it is moving up, if it is moving down, no, Kausalya, this is strike slip fault where you have the horizontal movement. But when you have this movement up or down at an angle, we call it as the dip slip movement. Okay. So we have a dip slip fault or dip slip movement. We have the strike slip fault or the strike slip movement. Then there is the third one, which is the oblique slip fault, which is basically a combination of both. So if you have two blocks, I don't know if you can see. Okay, let's say this movement is also there, and at the same time, this block 1 and then let's say this is block 2. So the horizontal movement is also there, and at the same time, let's say block 2 is moving above block 1. So such movements we call it as the oblique slip movement. So we have strike slip movement, we have dip slip movement, and a combination of both, which is the oblique slip movement. This is just I'm recapping whatever I had discussed in the previous class through questions, because it will be easier for you to recollect it, and if such similar questions come for your assignment or examination, it will be easier for you. So here I have again a video, I think. Yeah, so you can see this is how strike slip movement is happening. So this is the two-dimensional one, and that first one was the three-dimensional. So this classification, this is in San Andreas fault. So we are seeing a strike slip movement. This was a river which was going, it was supposed to go in this fashion here, but because of that movement, it got offset and its movement became like this. So this is a strike slip fault shown in the terms of the San Andreas fault. I don't think you have to go to detail regarding left lateral and right lateral, but the basic idea is, if suppose just for the basic like sake of knowing it, I'll just tell you. So let's say you have this block, okay. So I'm standing over here, okay, on this block, and I'm looking towards this block. So with respect to me, I'm looking at where that movement has taken place. So according to me, or else in this, okay, that is better. So this is one person is standing on this block and this block has moved over here. So this, according to this person, this movement is towards the left. And if the same person stands here, again they can see that the movement is towards the left. So we call it as left lateral. And then we have the right lateral. I think again I can show. So you can see I'll just erase this. So if you look at this, if you are standing on uh, one side and if you look on the other side and you see in which direction that movement has happened, so according to that you can say if it has moved to the left, you say it is left lateral movement, and if it has moved to the right, you call it as the right lateral movement. Now I'll show you an image. You need to identify what the fault type is. Okay, so you have different kind of fault. You have the strike slip fault, in which you have left lateral and right lateral. Then you have the dip slip fault, in which you have the normal fault and the reverse fault. So you have to tell me what kind of fault is present over here. These two images, a single type of fault is there. So please just think, and can you give me the answer? Both cases, it is the same kind of fault, but what is that fault? You can put the answer in the chat box. We have already discussed the different types. Yes. Okay, so Kausalya has given me the answer. So the answer is reverse fault. So if you can remember from my previous explanations also, I hope you can identify where the fault line is. Okay, so this is the fault line in this image, and in this image this is the fault line. So you can see where this, if you look at this layer and this layer, you can see there is an offset, right? So this block has moved in this direction and this block has moved like relative to that, it has gone down. So when this is the hanging wall, if you remember, on which like it is hanging on the foot wall. So this is foot wall, and similarly in the other image also I think you can imagine. So when the hanging wall moves up relative to the foot wall, which is very obvious over here, we call it as the reverse fault or the thrust fault if it is a low angle reverse fault. I hope the idea of fault movement and types of fault are clear to you, because it's when you, with regard to earthquake, it is pretty important. That's why. Even in this one you can see, right? This is block 1, this is block 2. So this is the hanging wall. 1 is the hanging wall and 2 is the foot wall. And if you can see, there is a slight movement only, but then this block has gone up and this block has come down relative to that. So this is a reverse fault. If it has been like if it had been a normal fault, then this hanging wall in case of the first image and this one of the second image would have come down. If the image was such, then this answer would have been normal fault. But in this case, both cases, the hanging wall has gone up, so we call it as the reverse fault. So this is not a very essential question, but I thought for the sake of understanding, I should put it here because I had explained it in the last session. So how does a reverse fault form? There might be some kind of external forces acting, because of which this reverse fault forms, that movement forms. So yes, as Kaushala has given, it is the compressional forces. So it results from the horizontal compressional forces. So if you have a block with you which has a fault line, and if you compress it from both sides, the compression is happening, then the movement associated with that will be a reverse fault. So this is often associated with the convergent plate boundaries, if you remember, where two plates are coming towards each other. They can subduct and they can collide. When they collide, as in case of Himalayas, we see a lot of reverse fault has formed in the Himalayan mountain chain. So the hanging wall moves up the fault plane relative to the full foot wall because of this horizontal compressional forces. I hope that idea is clear to you. You don't have to go to much detail, but then this is the basic understanding. That's it. What is the name of the theory which explains the energy released during an earthquake? I had discussed this in the last class, last session. So those of you who can remember, what is that name of the theory which explains the energy released during an earthquake? Anybody? I think I had mentioned it in today's class also. Like there is the theory which explains the energy released during an earthquake. I had given you an example with a rubber band also in the last class, like how when you stretch a rubber band, when you release it, and all those things. Okay, so for those of you who know, it's fine, but for those of you who doesn't, it's known as the elastic rebound theory. So that's why I gave you the example of the rubber band. So if it is stretched and then released, so that energy is accumulated while you're stretching it, and when that comes to a limit and you release it, it bounces back to the initial state. So I think I have, yeah. This video is a very good depiction of that. So you can see this road bending, right, with the fault movement. It was bending, and then suddenly when that rupture happened, or when that energy release happened, the road became like came to two sides. So I hope that is clear to you. For those of you who didn't understand, it's just I can play it again, I think. So you can see the road is intact in the first case, it is slowly bent, and then when the energy is released, you can see how the road has gone to two sides, but then its initial shape has been restored. This is elastic rebound theory. So this is the fall zone, and along which the movement is happening, and then so for somebody who is just seeing this uh, road for the first time, they might think that like that is intact because its shape has not changed, but its position has changed. That is elastic rebound theory. Name the two broad classes of seismic waves which I had discussed today. So you can just give me the name. Two broad classes. I don't need the detailed classification, just the two broad classes. Yes, body waves and the surface waves. So body waves you have P and S waves, and surface wave you have Love and Rayleigh waves. What is the difference between a seismograph and a seismogram, which we had discussed today also? And for those of you who joined late, if you want me to repeat anything, you can ask me. Otherwise, if you know the answer, please give me the answer. What is the difference between a seismograph and a seismogram? I had yeah, so as Kausalya has said, seismograph is an instrument and seismograph is an instrument and seismogram is the graphical representation of that P, S wave and all, amplitude versus time. How is the location of an earthquake determined? So I had shown you an example also, a diagram I had shown. So how the location of an earthquake is determined. So the P and S wave, which are essentially the body waves, their arrival times are recorded by different seismographs, and that is used to determine the location of the earthquake. So if you remember the previous image also, you would remember that let's say if this is where seismograph 1 is there, this is seismograph 2 and here seismograph 3 is there. So in all these three locations, like at least three location data we need. That is what the basic thing is when it comes to determining the earthquake location. So you have three locations which has seismograph recordings, and then you'll see the P and S wave arrival times. So you know if you like that the P wave will arrive first and then it is followed by the S wave. So they will look at this time difference in all these three locations. Then based on that data, they will consider the radii of three circles. So let's say one circle is like this. The second circle, let's say, is like this. And the third circle might be like this. Anyway, so the point where all the three circles intersect will be your earthquake's location, point of origin. So this will be a bit more clear for you with this. It's known as triangulation. So I hope that has cleared your doubts regarding how the epicenter of an earthquake is located. Moving on to the next. What do you mean by seismic retrofitting? Which we discussed towards the end of today's class. So what do you mean by seismic retrofitting? Or why do you do seismic retrofitting? That is also. Anybody? I don't need the exact terminology or anything, just what do you understand by this? Okay, so seismic retrofitting is the strengthening of a structure to make it more resistant to earthquake shaking and damage. This can be done in any kind of way. You can bolt the structures to the wall, you can bolt the foundation of the building, you can, bolt it to the foundation of the building, anything. So basically, you are strengthening a structure to make it more resistant to earthquake shaking and damage. What is tectonic inversion? This is from the previous class, but since I had seen a few slides related to this in week 4, that's why I had put it here. So what is tectonic inversion? This is related to the fault movement, the reverse fault, normal fault, all those things. You can just give it a try, like just from the name, can you figure out like something is getting inverted, like how it should normally be? From that, some change has happened. So, what is tectonic inversion? Yes, so that is basically uh, reverse faults are formed, not exactly, okay, I'll give you the definition. So, process where the extensional normal faults are reactivated by compression. So, what it means is that normally, like in a normal scenario, you will get a normal fault because of extensional forces. So, somebody, let's say you have a paper, okay, just imagine you pull it from both sides, so it tears down the middle, or anywhere where tension is more, anything. So you are extending it and it is breaking. So that is not extensional normal fault. So normal fault is where the hanging wall moves down relative to the foot wall. So that happens when you extend from either side of the blocks. That is it. So normal faults are always formed by extension most of the time, but in case where such normal faults are again reactivated, like they moved and they're just like that, staying like that, but they get reactivated by compression, which is not a normal scenario, right? That is not how normally normal faults are made, but in this particular case, they are reactivated by compression. So, only thing you have to keep in mind is that generally, normal faults are associated with extensional forces and reverse faults are associated with compressional forces. So, in case of tectonic inversion, what happens is extensional normal faults or compressional reverse faults are reactivated by compression or extension. That is, extensional normal faults are reactivated by compression and compressional reverse faults are reactivated by extension. That is known as tectonic inversion. I hope that is clear to you, because sir has given you an example from the Kutch region. That's why I had put it here, because possibly I also don't know how the questions for your exams are put, but then if they ask this, you can give the answer in this manner. This is a very simple depiction of what a tectonic inversion is. So this is an image also. So I had shown this in the last class also. So here you can see, right, if this is the normal situation of that area, then after a period of time you are having this crustal contraction, and contraction or compression will result in thrust faults or reverse faults. So you can see this is moving up, this is moving up. So you have two blocks like this. So they were staying like that. But then uh, later on, some crustal extension happened, which kind of reactivated that fault. So the fault got reactivated, and it, see, this crustal extension reactivated the fault. Similarly, in this one also. So Kutch region, it is characterized as the dash region, but it falls in seismic zonation dash, which means the area is seismically very active. So considering the position of Kutch and all those things, we call Kutch as something. But in terms of seismic zonation, 2, 3, 4, 5, right? That is the seismic zonation. It comes under one of these numbers. What is that number? And uh, like I'm leading you to the answer, so give me, like those who know, you can give me the answer. Like in seismic zonation, what number does Kutch comes in? Which tells you that it is very active, seismically very active. This is a very straightforward question. If you know what seismic zonation is and how that scale is, you can understand this. Yes, so the answer is 5. So it is a stable area considering its position, but then because of the earthquake events due to the faults present there, it is characterized as, it comes under the seismic zonation 5. The cohesive-less nature of sediments from the combination of dash and dash led to the formation of sand dikes during liquefaction. So cohesiveless means something which doesn't stick to each other. So what kind of, okay, I can't give you the answer, but what kind of sediment is cohesiveless? That is the answer for this question. So the answer is sand and silt. So sand, silt and clay, right? So in this, if you look at the grain size distribution, if you look at that, so clay minerals, like clay sediments, they are like very, very fine grained and they will easily stick, right? If you hold clay in your hand, how soft it is and how easily with water it will mix, and you can just hold it and crumble it, like you can press it, all those things. But when it comes to silt, it is slightly more coarser than clay, but not that coarse. But then it will not, stick, or basically it doesn't have this cohesive nature. And sand means even more coarser grains, and they will not stick. So in cohesiveless nature of sediments from the combination of sand and silt, it leads to the formation of sand dikes during liquefaction. So when you have an area which is, let's say, overlain by a cohesive layer such as clay, and underlying under that you have this combination of sand or silt, for that matter, and then if some pore water pressure is there and all those things during an earthquake, it can create a crack through the clay layer on top and come out as sand dikes, or the sand boils that you had seen in the video that I had shown you before. So cohesiveness, if somebody says, that is basically the ability of these grains to stick to each other in the presence of water. So with dash in the thickness of the dash layer, more ground acceleration would be required to liquefy the sediments. So with increase or decrease, that you have to tell me, in the thickness of the which layer, like top layer or bottom layer, more ground acceleration would be required to liquefy the sediments. If you don't know the answer as such, you can actually think about it also and then give me an answer. Like if you're not already familiar with this. The thickness is right, but what I'm saying is with increase, like the first blank, you have to tell me with increase in the thickness or with decrease in the thickness. Like increase or decrease, that you have to tell me. And in the second part, you have to tell me the top layer or the bottom layer. Like that is the option I'm giving you. Thickness is fine, but what like increase thickness or decrease thickness, that I have to know. Okay, and what about the other part? Which layer? The top layer or the bottom layer? Or like whatever terminology you want to use. Okay, so the answer is not decrease, it is increase in the thickness of the capping layer. Capping layer is the top layer. More ground acceleration would be required to liquefy the sediment. So I think I have, yeah. So if you look at this image, okay, so you have on the left, you have a thin, this A is the capping layer, okay, so that is the non-liquefiable low permeability capping layer, which is basically, you can say it might be clay, let's say. So A is that and B is the liquefiable layer. So if this top layer is thin, like its thickness is less, as in the first case, that will not require so much of ground acceleration to liquefy the sediments because the bottom layer is thicker. So it can break through the top layer. That is the thing, which you had seen in the sand boils or sand dikes, sand blows, all those things. But if you look at the second image, in this, the top layer or the capping layer is thicker compared to the this bottom layer, okay, or the liquefiable layer. So in this case, in order for that bottom layer to break through and come out of this top layer, that requires a lot of ground acceleration. Like that movement should be so extensive that the bottom layer, the liquefiable layer, can come on top. So that is the difference. So if you can just keep this image in your mind, then that will help you in answering such questions. So the capping layer or the top layer, if it has increased thickness, the ground acceleration will be more for the sediments to liquefy. But if it has a very less thickness or decreased thickness, then the bottom layer or the liquefiable layer can be easily liquefied based on like with less ground acceleration. I hope that is clear to you. I just drew this image so that that pictorial memory is there for you. That's why. So A and B. I hope you have understood. Or if you have any questions, you can ask me. Okay, so this brings us to our next question. So increase in the dash results in sudden movement of sediment blocks causing something. So you have to associate this question with earthquake and think on that grounds and give me the answer. What will increase which will result in the sudden movement of sediment blocks, which eventually results in something else? Think in terms of earthquake because your topic is on earthquake. Okay, so since okay, the answer is pore water pressure, and that is increase in the pore water pressure results in sudden movement of sediment blocks causing lateral spreading. I had asked this in the previous part also, right? What lateral spreading, like because of soil liquefaction, the pore, like because of increase in pore water pressure, soil liquefaction will happen, and as a consequence of soil liquefaction, lateral spreading will occur. So this is an image. So before an earthquake, so this is the capping layer, the dark brown layer, and the yellow layer is the liquefiable sediment. So this is before the earthquake. But then after earthquake, what happened? This layer got liquefied, but the capping layer is a bit more intact. So it got broken into different blocks. And here you can also see this plugs, right? You might have seen the real life example in the lectures also. Liquefaction features caused by an earthquake of around 7 magnitude would be around dash of kilometer. Like what I'm trying to ask is, if the earthquake is of magnitude 7, then how far can you see the liquefaction features in that area if the magnitude is 7? You can think this in terms of that amplitude increase that I had discussed. I can give you the options also, like tens of kilometer, thousands of kilometer, hundreds of kilometer, or none of the above. Okay, like 7 magnitude earthquake is a pretty strong earthquake. Okay, so the answer is hundreds of kilometers. So the explanation I can give you with the help of this diagram. So this is the magnitude that we are saying. So this is the epicentral distance. Okay, so where that epicenter is. So from the epicenter, how much it can spread. So if you look at this, you can see the 7 magnitude earthquake. If you just extend it, you can see almost like hundreds of kilometer epicentral distance is there. So in that case, it can cover, like that is the maximum that we are talking about. At least that much distance the liquefaction features can cover, or they can spread around. So that brings us to the end of the presentation on my part. But if you have any question, because a few of you had joined late also, but I don't mind repeating it now or in the next class, I don't mind. But if you have any questions, please ask me. Don't hesitate. We had discussed about seismic waves, different types of seismic waves. Then we had discussed about seismographs and seismogram also, and then earthquake location, which I had shown in this image, and then I had also shown you a video. Then the earthquake intensity regarding the Mercalli scale, then the magnitude, the Richter scale, then how earthquakes are predicted, like different ways how earthquakes can be predicted, the probability of earthquake, the earthquake risk assessment, minimizing the earthquake damage. So if you have any question from any of these parts, please ask me. You can just clear it in these sessions. Or if you want to repeat any, like want me to repeat any topics in the upcoming part, like from the previous classes also, I don't mind. Just let me know in advance so that I can do it. Any further questions? Shall I stop sharing the presentation, or do you have any queries regarding the presentation? Okay, so I think I can end the presentation. I'll stop sharing it. So any questions, anybody? Because when I started, only few were there. I'm seeing some more people. That's why I'm asking. Like, if you have any questions from this week or previous week. Okay, so if there are no further questions, then I guess we can end today's meeting. Thank you for patiently listening to me and then responding for those who responded. And I would urge the rest of you to participate so that it's easier for you also. So if there are no further questions, okay, then we can end the meeting. Like, you can exit. Okay, thank you.